Have you ever stretched a rubber band and watched it snap right back to its original shape? Or maybe bounced a ball and seen it deform slightly before springing back? What about the springs in your car's suspension, or even the way your shoes flex as you walk? These everyday occurrences are all thanks to a fundamental property of materials. It's a property that allows things to bend, stretch, or compress under force, and then return to their initial state once that force is removed. It's absolutely everywhere, and it's crucial for how countless objects and structures behave. Without it, bridges wouldn't handle traffic, buildings wouldn't sway safely in the wind, and your favorite stretchy jeans wouldn't be, well, stretchy. This incredible property is called elasticity, and understanding it unlocks a deeper appreciation for the world around us. So, what exactly is elasticity? In simple terms, it's the ability of a material to deform reversibly. When you apply a force to an elastic material, it changes shape or size. But here's the key. When you take that force away, the material goes back to how it was before. Think of it like a tiny internal spring within the material. You can push or pull on it, but it always wants to return to its relaxed state. This is a temporary change, not a permanent one. At a microscopic level, materials are made of atoms and molecules held together by bonds. These bonds act a bit like springs. When you apply a force, you're slightly stretching or compressing these bonds. As long as the force isn't too great, the bonds can handle the deformation. When the force is removed, the attractive and repulsive forces between the atoms pull or push them back to their original equilibrium positions. This is why the material recovers its shape. To talk about elasticity scientifically, we use two important terms: stress and strain. Stress is a measure of the force applied per unit area on a material. Imagine pushing or pulling on something. The stress is how concentrated that force is. Strain, on the other hand, is the measure of how much the material deforms relative to its original size. If you stretch a rubber band, the strain is how much longer it got compared to its initial length, expressed as a ratio or percentage. For many elastic materials, especially metals and other solids within certain limits, there's a simple relationship between stress and strain. This relationship is described by Hooke's law. It states that stress is directly proportional to strain. This means if you double the stress, you double the strain, and so on. The constant of proportionality in this relationship is a measure of the material's stiffness, known as the elastic modulus. A higher modulus means the material is stiffer and deforms less under the same stress. Hooke's law and the concept of perfect recovery only hold true up to a certain point called the elastic limit. This is the maximum stress a material can withstand before it starts to deform permanently. If you apply a stress beyond the elastic limit, the material enters the region of plastic deformation. In this state, even if you remove the force, the material will not fully return to its original shape. It will be permanently deformed. Push it too far beyond this, and the material will eventually fracture or break. Elasticity isn't just about stretching. Materials can be subjected to different types of forces, leading to different types of deformation. We have different elastic moduli to describe these behaviors. Young's modulus, perhaps the most common, describes a material's resistance to stretching or compressing along a length. It's relevant for wires, rods, and columns. Shear modulus describes resistance to twisting or sliding deformation. Bulk modulus describes resistance to changes in volume under uniform pressure, like squeezing something from all sides. Each modulus tells us how stiff a material is under a specific type of stress. Elasticity is not just a physics concept. It's fundamental to engineering, design, and countless technologies. Engineers rely on understanding elasticity to build safe and reliable structures like bridges, buildings, and aircraft. They need to know how materials will behave under load and ensure they stay within their elastic limits. In manufacturing, elasticity is key for processes like stamping, bending, and forming metals. In product design, it influences everything from the feel of a phone button to the performance of sports equipment like tennis rackets or running shoes. Even in nature, biological tissues like skin, muscles, and tendons exhibit elasticity, allowing for movement and flexibility. From the smallest spring in a watch to the massive steel beams in a skyscraper, Elasticity is a property that enables function, safety, and durability. It's a constant, invisible force working all around us. Understanding elasticity helps us appreciate why materials behave the way they do. It's a simple concept with profound implications, shaping the objects we use and the structures we inhabit every single day. It's truly an amazing part of the physical world.